Along these lines, we have many more registers. For example, at offset number 4, right, we have something called UART RSR and UART ECR, once again read write registers. Over here it says clearly that after reset the value is known to be 0. In other words, if you were to read out from address number 4 at immediately after reset, you would find that the result is going to be 0. This is the receiver status register or the error clear register. So, it makes sense that immediately after reset the value is going to be 0. There were no errors because nothing has been received, no errors have been declared so far. Therefore, immediately after reset the value is going to be 0. It also has a width of 4 for reading and a width of 0 for writing. In other words, writing into this is not really, there are no bits that it is going to respond to. I am not going to go into the details of each and every individual register, but I would strongly encourage that you look through it and try and understand what this data sheet actually implies. Now comes the interesting part. By the way, just to repeat, right, you see that this address over here is 0, the next valid address is 4. So, in other words, it corresponds to 4 bytes later, which basically means 32 bits, right. So, each location out here is considered a 32 bit location. You might use only 15 or only 16 of them or only 8 of them, but it is a 32 bit location that is being reserved and each address increment is typically by 4. And therefore, we see that the next address that we have is from 8 up to 0x014 in hex, right. So, this is not really 14, it is not 14 decimal, it is actually 14 hex, which is 20 in decimal. So, from address number 8 to address number 20, right, the addresses are reserved. Once again, do not try to write anything into those addresses, do not rely on data that you get back if you read from those addresses, and ideally do not even try to read from those addresses, because as we will see later, just reading alone could potentially have a side effect. Same way 0x018, which is 24 decimal, then 28 decimal and so on and so forth, right. We find that once again at 32 decimal we have some other low power counter register and so on. The interesting thing you might, and yeah, so let's just look at the register at 0x018, right. It is a flag register and you can see that it has one sort of a strange behavior immediately after reset. So, let us go in there and try and understand what is happening. So, in the flag register what it says is there are a number of bits inside that flag register which have certain kinds of specific functionality. First thing it says is the bits 15 to 9, right. So, it is essentially treating it as a 16 bit value, even though looking at it purely from the address point of view, this is a 32 bit address range that we are looking at, right, but it assumes that you are going to get back only a 16 bit value, and therefore, it says 15 to 9 are reserved, do not modify. In other words, do not try to write to these bits, read as 0, right. So, the read as 0 is actually telling you that maybe in this case reading from this register is safe, right. What will happen is that you are going to get back zeros in these bits. Now, given the fact that this is reserved, you should not in general rely on the fact that this is going to be read back as 0, right. So, ideally what you do is as soon as you read back something from this UART FR register, what do you do? We use the bit masking techniques, right, that we saw in the embedded C programming. We create a mask which will get rid of the top 7 bits and retain only the others, right. Now, the other bits, for example, bit number 8 is something called a ring indicator, and ring is something more from the time when UARTs were used for modems, which were used for actually communicating data over telephone lines, right. So, there would actually be something to indicate that yes, the line is ringing and that the UART probably needs to answer, respond and start setting up a communication link. There are other bits. TXFE, for example, stands for the transmit FIFO empty, meaning that there is no data currently in the FIFO, and that usually means it is safe to write new data into it. And of course, the FIFO itself could either be disabled or enabled, and the behavior of the TXFE bit is modulated according to that. RXFF stands for receive FIFO full, and this is something which, just like we looked at in the case of the valid and ready handshakes that are used for the AXI protocol, pretty much all communication protocols use some kind of handshaking. In our case, the RX FIFO, right, is going to indicate that it is full and cannot accept any more data by indicating that this particular value is 1, right. Similarly, you can also have a transmit FIFO full, which tells you don't try to write any more data, the transmit FIFO is currently full and you have not managed to send out the data corresponding to this yet. Similarly, RX FIFO empty, then there is a busy signal, a data carrier detect, which like I told you corresponds to when these things are used as modems over telephone lines. Data set ready, clear to send. These are, in other words, signals that were used for various kinds of handshaking and negotiating between the two sides of the communication interface, right, about whether or not it's okay to send data. So, UART FR, in other words, is an interesting kind of register. It does not have an 8-bit block of data. Each individual one, bit number 8, bit 7, bit 6, bit 5, each and every one of these has a separate functionality, and the functionality of each one of those can be controlled separately, right. And this is very common across many such systems, right. So, now with this in mind, if we just go back and look at the reset state of what was there in UART FR, you will notice that it says that by default it would start off with the initial bits in some unknown state, but then some bit number is 1, then 2 of them are 0, then there is a 1, then a 0 and so on. So, if you want to understand that, you need to go in here and basically look at this, right. Yeah. So, if you look at the meaning of the bits, you will see, for example, that as soon as you have come out of reset, you can probably expect that the busy signal corresponding to the UART should be 0. In other words, the UART should not claim to be busy as soon as it has come out of reset. If so, there is a problem. That is okay, that is easy to understand. But then look at something like RXFE. This basically indicates that the receive FIFO is empty. Now, if this was 0, that actually indicates a problem, because what it is telling you is that the system has just come out of reset, but the FIFO is not empty, because after all 0 indicates false. So, instead of that, what we have is immediately after reset, this particular bit, bit number 4 and similarly bit number 7, you can expect that they will come up as 1 immediately after reset. The full bits, on the other hand, TXFF, RXFF should come up as 0, because the FIFO should not be full immediately after reset. And when you go and look at the actual bit locations out here, you can see that in fact, right, bit number 4 and bit number 7, which correspond to the two empty signals, are in fact 1 after reset, but the two in between them, which are the FIFO full signals, turn out to be 0 immediately after reset. So, as we know, when you bring up a system out of reset, whenever you are writing Verilog, you should have an always at POS clock or neg clock, as you might choose. Immediately after that, you should have a condition which checks for what to do with reset, right. Depending on whether it is a reset active high or active low, you need to decide for each and every bit that is present in the system, should the bit come up as 0 or as 1. The common case is that we assume that it is going to come up as 0, but what this indicates is it is entirely okay to also have some of the bits come up as 1 after reset. Alright, so let us go further with this. Like I said, there are other addresses. Address number 28, for example, is reserved. Address number 32 has some other low power counter register and so on. Each of these has a different width, a different amount of data associated with it, and you can keep going down this line until suddenly we hit one chunk out here where we see that from 0x04C to 0x07C, which is quite a large chunk of addresses when you go and actually do the computation, the whole thing basically says it is reserved. In other words, this is roughly because 40 in hexadecimal would be around 64, so 4C would be somewhere around 70 thereabouts, and 7C would be somewhere around 120, somewhere around that. So, there is a chunk of nearly 50 addresses that are unused, or rather they are reserved, okay. And then you will see that there is another set of addresses 80 to 8C, which is reserved for test purposes. Now, what this says is you might actually see some kind of behavior if you write to it or you read from it, and you cannot guarantee what is happening, because this is meant only for the manufacturers, the people who coded this system, to debug what is happening inside the UART peripheral. and they are not planning to sort of make that information public. They want to keep it for their own debugging. Why you need to be aware of this is, if you decide that okay, you know, I don't care about, they are saying it's reserved, it must be that they are just ignoring the values. Well, in these particular addresses it's also possible they are not ignoring the values. It might actually change the behavior of the system in ways that you do not know because it's not documented in the data sheet. After that, you can see that there's actually a huge chunk of addresses, right? If we do the calculation 0x090 up to 0xFCC, right? This is almost at beyond 4000 at this point, right? So this chunk of addresses from around 140 up to nearly 4000 or thereabouts is reserved, right? And then there is another small chunk of addresses which it says reserved for future ID expansion. Once again, right now all that you can say is okay, you shouldn't be using those addresses. And then there are a whole bunch of different peripheral IDs and cell IDs, all of which correspond to different kinds of behaviors that are defined as part of the data sheet of the system. So this essentially shows you how we made use of, so you can also see that the very last address 0xFFC corresponds, FFC corresponds to the decimal number 4092, right, and that essentially says that this is the very last 4-byte location that you can read or write from. It also says that if you were to, this is a read only register, and if you read from it you will get back this value 0xB1. All of this, these last set of, you know, the IDs and the cell IDs that you have over here are all read only, right, and indicate some kind of information about the manufacturer. The fact that ARM has built it and they intend to use it for certain kinds of purposes, all that information is what is encoded in here. So if somebody goes and reads from these addresses, they should be able to interpret it and say okay, this was essentially manufactured by ARM and is being used within this context. The idea is that if a different vendor manufactures it, usually they would have a different kind of peripheral ID, cell ID and so on, but follow a very similar kind of register map, so that a driver, a software driver that is written for interfacing with this UART can now connect with that, read from certain locations and understand who built it, what it was used for, or perhaps some information about, you know, the version number or other kinds of useful things that you have out here. So we have looked at the summary of the registers present in the ARM UART peripheral, and what we looked at was just a brief listing, right, to quickly understand the nature of the registers. But as we also saw for some of the examples, you can go into detailed per register bitwise information, right. All of that has to be provided as part of the data sheet because it's all necessary for the end user, the person who is actually trying to write software to communicate with this peripheral.